Let's take a look at balancing equations. We'll use the combustion of propane as an example. C3H8, a gas, propane, can react with oxygen in a combustion reaction to give CO2 and H2O. The reaction equation given here is an unbalanced equation. To make sure that the number of each individual atom on the left is equal to the number of atoms on the right, we must balance its equation. We need to do this because we recognize the law of mass conservation. We must have the same number of atoms on the left as on the right in order to conserve mass. We can start off by looking at the number of carbons. On the left there are 3 carbons, whereas on the right there is only 1. So let's start by balancing the carbons. We can do this by putting a figure 3 before the CO2. This multiplies the 1 carbon in CO2 by 3 and balances it with the 3 carbons on the left. Next we look at the hydrogens. There are 8 hydrogens on the left, but only 2 hydrogens on the right. We need to balance the hydrogens. We can do this by putting a multiplication figure before the H2O. If we use a 4, we multiply the 2 hydrogens in the H2O by 4 to give us 8, which balances with the 8 hydrogens on the left. Next we look at the oxygens. There's 2 oxygens on the left and 3 times 2 oxygens from the CO2, which is 6, plus the 4 oxygens from the H2O. This means we have a total of 10 oxygens on the right, but only 2 on the left. Therefore, we need to balance the oxygens by multiplying the number of oxygens on the left by 5. This means we now have 10 oxygens on the left and 10 oxygens on the right. Overall, now we have a balanced equation. It's always worth checking through when you balance an equation to make sure you haven't changed any of the other atoms in which you already balanced before. So let's go through this. We have 3 carbons on the left and 3 carbons on the right. We have 8 hydrogens on the left and 4 times 2, which is 8 hydrogens on the left. We have 5 times 2, or 10 oxygens on the left, and 3 times 2 plus 4 times 1, which is 10 oxygens on the right. So this is a balanced equation. We can now see, using this balanced equation, how many moles of propane will react with how many moles of oxygen. We can see if we have 1 molecule of propane, it needs 5 molecules of oxygen to react completely. This means that 1 mole of propane will need 5 moles of oxygen to react completely. This brings us to the concept of limiting reactants. On the left-hand side of a chemical equation we have the reactants, and after the reaction, on the right-hand side of the chemical equation, we have the products. If we had 2.3 moles of propane and 8.12 moles of oxygen, let's see how these would react. We know that 2.3 moles of propane needs 5 moles of oxygen for every mole of propane. So we can use this molar ratio taken directly from the chemical equation on the left-hand side to calculate how many moles of oxygen we need to react 2.3 moles of propane completely. The moles of propane cancel, and we get 11.5 moles of oxygen needed to react completely with 2.3 moles of propane. We only have 8.12 moles of oxygen. This means that the reaction will be limited by the amount of oxygen available. Oxygen is therefore considered the limiting reactant. We would need more oxygen to get the reaction of propane to go to completion.